So, hello everybody. I am Gerald Baeza. I'm the software architect in STM32 MPU team. And today I will do this talk with Etienne.
Hello,
welcome Etienne.
Etienne Carriere. So I'm a software engineer at ST and working with Linaro teams. And so Gerald will present you this STM32 MP1 trusted boot chain. Go ahead, Gerald.
Okay, thank you, Etienne.
Forgot to mention, yeah, if you have questions, but there are not too many. If you have questions, do not hesitate to put in while we talk, and we try to address them during the talk or after. Go.
Yeah, and I think we will have some time to speak directly. So as you said, today we are going to speak about the trusted boot chain on STM32 MP1 series, showing you how it is implemented and what can be done on this platform. So as a first step, I will give a short overview of what is the STM32MP15. Then we will jump to the main topic, I would say, that is the boot chain description. After that, we will have a short parenthesis about what we call the firewalling, so the way we can isolate things on the platform between the secure and non-secured world. A short conclusion, and then it will be the right time to raise questions that will still be open after the presentation. So let's talk about the STM32MP15, and 7 means that this is a superset on this family. So just a few words to say that this is a SoC embedding a dual Cortex A7 able to run at up to 800 MHz. And together with this dual Cortex A7, we have a Cortex M4 running at around 209 MHz that can be used for all the real-time aspect or to offload some activities from the main core. Around this, we have many peripherals. So for those among you who know the STM32 MCUs, you will find many peripherals inherited from these families and other peripherals that are more specific to microprocessors, like the GPU, for instance. So we can continue with the boot chain. So what we call the boot chain on such a platform is all the execution that will take place at startup in order to initialize the various hardware execution context we have on the platform. So on STM32MP15, we have two hardware execution contexts corresponding to the Cortex A, because the Cortex A is able to run in secure mode or non-secure mode. And we have one execution context for the Cortex M, because the Cortex M only knows the non-secure world. So the boot chain will install one firmware in each hardware execution context, and this firmware will serve the application all along the runtime. In this slide, we can see the several stages that we can identify in the boot chain. So before digging in detail here, just one comment on the top here on the right, you can see some articles named that correspond to the articles in the wiki on STM32 MPU wiki, where you will be able to find such diagrams and more information if you want to come back on this later on. So let's describe this boot chain. So when you put the power supply on the platform, first it will execute the ROM code, that is the part embedded directly in the STM32MP1. The ROM code will load and jump to what we call the FSBL, first stage bootloader. The first stage bootloader will load what is there, the second stage bootloader on the non-secure side, SSBL, and then it will load the secure monitor, and it will jump to the secure monitor to run the secure monitor in the secure context. And on non-secure side, what we will have after is that the second stage bootloader will load Linux OS, that will be here to execute the application for the non-secure world. On the right, you can optionally load the Cortex M, optionally, because some user may not want to use it, so it is optional. And this loading can be done whether from the second stage bootloader or from Linux OS. The choice between one option or the other will depend on the time that you want to spend before getting the coprocessor alive, or on the other side, the close cooperation you will want between Linux and the coprocessor. This is a summary of what could drive you to opt for one option or the other. Then let's describe and tell a few words about trusted firmware for Cortex-A terminology. So trusted firmware for Cortex-A, that is called TFA. Maybe you already heard about that. In this terminology, each stage is described by acronym that are BL and a number. BL stands for bootloader. So the ROM code in our case can be seen as the BL1. After that, the first stage bootloader would be the BL2. The secure monitor, the BL32. And the second stage bootloader on unsecure side, the BL33. It is important to have this acronym in mind if you dig into TFA documentation, because this is what is used widely in their documentation. And then in this slide, we jump to what are the components really used in our distribution, in OpenSTLinux distribution that we are delivering with STM32 MPU series. So as BL2, we are directly using TFA BL2, meaning that we are taking the BL2 from trusted firmware from Cortex-A source code that you can find here. The secure monitor we are using is OPTI, Open Portable and Trusted Execution Environment, with the source code available on Git here. Then our non-secure bootloader is U-boot, the famous U-boot that you can find on the Deng's source Git, and Linux OS that you can find on this Git. Now, Etienne will give you more information of what we call the trusted boot chain and the chain of trust.
Okay, thanks, Gerald. So we start from this architecture where we have those several boot stages, and those boot stages are in charge of loading the next stage, or the final OSs are in charge of loading and running applications. And for all this to be trusted, they have to be related to a root of trust of the platform. And so we'll explore how the root of trust is used and accessed in this boot scenario. So all start from the call boot, where we just call or one boot, actually, where we just reset the cores, and cores execute the ROM code. And the ROM code, well, in our case, is a hard-coded code in the system on chip itself. So it's known to be secure, and this ROM code will get the BL2, the first stage bootloader image, and it will authenticate it using OTPs read from the platforms. So this is where the ROM code has this link to the root of trust of the device to load the first stage bootloader. So this first stage bootloader is in charge itself of loading and booting the next stages. And so the next stages are the secure world and the non-secure world. So to do this, our preferred boot chain, the BL2 uses the trusted firmware FIP format, which stands for firmware image package, which is just a way to have several images into a big blob, and also to have relations between images and their certificate, so that we have means to authenticate this certificate. And the way the root of trust propagates here is that there is a root certificate in the FIP, which is checked by BL2 against the root of trust of the platform, which is the some OTPs. So here the FIP is validated thanks straight from the root of trust of the platform. And so BL2 with this FIP loads the secure world and the non-secure world. So first the secure world, BL2, TFA BL2 will load the OPT image. And the OPT image itself so gets this trust delegation because it's booted being signed and authenticated at boot time by BL2. And OPT also accesses some root of trust of the platforms, especially for handling all the trusted applications it will later load and execute. And so these trusted applications and their isolations are based on two root of trust, which are UTPs, specifically to isolate the secure storage related to the trusted applications. And although the TA binaries itself, when they are loaded from an insecure world, they are authenticated, and the authentication is based on the public key that is built in the OPT image. And so this part of the public key gets is in the chain of trust since the BL2 boot stage and the authentication of the OPT image itself. And so the BL2 has done the work for the secure world, which is able to load applications at runtime and to isolate them. And this BL2 will also load and boot the non-secure world, which is the U-boot. So U-boot is also an image that is contained into the FIP package and authenticated the same way as the OPT, based on some private key, but all in the end, all remaining to this FIP root key, root certificate that is bound to the root of trust of the platform. And U-boot itself can be used to authenticate the image it loads itself. So in U-boot, we can use the FIT format, which is a flattened image tree format, which is about the same thing where U-boot will load several images, and those images are themselves bound to certificates which shall be checked. So this is the way you would natively authenticate the Linux OS before it boots it. A word about the coprocessor, because the coprocessor, can be loaded and booted from U-boot or from the Linux OS itself. Actually, it can be done, and the same way we can use FIT, the firmware coprocessor image could be authenticated with FIP. We also have a way to have this authentication being done from the OPT and relying on some secret or something authenticated from the OPT itself. That was for the coprocessor. And for the Linux OS, usually, well, the Linux OS could authenticate and check its own user space, and usually this is mainly driven using, well, the native kernel isolation support and some especially device mapper when needing to add some security into the media and the file systems like DM Verity, DM Integrity, and those used in some distributions. So that makes the whole chain of trust of the platform. And actually, we have an Android release for this platform, and the Android chain of trust follows the same steps using the OPT and using notably the Android verified boot support, which is an OPT feature that U-boot invokes. So actually, OPT is used both at boot time discussing with U-boot and in initialization time discussing with Linux. So to archive this, so we have those two worlds, just a short word about this secure world. We have this secure world that is instancized, and we have a non-secure world, and by definition, the platforms hold some resources that can only be assigned either to the secure or to the non-secure world. And it happens that these resources are actually used by both, starting from the CPU themselves. the CPUs are where both U-boot, Linux, Opti will execute. So we have to share some services to manage this resource. And talking about the CPU, but we could talk about other platform resources as clock, regulator, reset controllers, and things like this. So the secure world embed a series of platform resources driven from some specification, mainly the PSCI specifications that is used in all the ARM Cortex-A family, and that is a de facto standard even for the 32-bit machines. So we use, sorry, I said PSCI for all the CPU power support. We are developing and working with Linaro and ARM to broader use of the SCMI specification, which is an interface specification that allows to abstract system resources like clocks, regulators, power domains, things like that, and to abstract them between two firmwares, and where we use the secure world to host the real effective clock accesses, and the SCMI client just has for clocks and does not have straight access to the hardware resources that are controlled under the control of the secure world. And we have some platform-specific SMCs, those silicon platforms, SMCs, specifically for services we have in our platforms, like OTP accesses, when all the non-secure, all the OTPs assigned to the non-secure world are used, and there are some unused in the secure world, and we have means for the non-secure to use those extra OTPs. And of course, with this setup, we have all the native Opti services, which start from loading and invoking a trusted applications, and all other services that have been implemented in the Opti or as trusted application in the Opti project. Worth to mention an alternate boot chain, an alternate boot sequence in the next slide, which is looking at another, next slide, Gerald, the one that was, okay, this one is another alternate boot sequence regarding the preferred one we showed before. And in this scheme, we are looking at using the UEFI standard to have a more standard way for an OS to install and to interact in an ecosystem. And it's something that also Linaro is working on, especially in this project around trusted substrates. We put some links in the slide. And so in this setup, we basically have the same boot chain that before, but that the U-boot this time is also embeds a UEFI implementation for some runtime services, and also a UEFI implementation for some runtime services. Did I say boot time or runtime before? So boot time services, sorry, implemented in U-boot and use that boot time. And the UEFI stack makes some code being resident and acts as a third runtime service for UEFI. And UEFI is something that is highly used by standard distributions for the distribution maintainer to operate on the devices and updates. And with this scheme, also using the Opti in the secure world, the UEFI stack itself can have access to some secure service from the Opti, both at boot time and at runtime. And of course, Linux OS also has those Opti service at runtime. So it's a good scheme that we explore and would like to archive. This is also related to a specification that is called EBBR, for embedded base boot requirements, which is a specification from ARM. We put the links, the reference here. And it's a specification that aims at having all the embedded devices category of ARM device SOCs that conform to the same way of providing OSs. And so these EBBR specifications just enumerate all the thing that such an embedded device could have to be compliant with this spec, which comprise some UEFI services, boot times and runtime service. So you can have a look at the EBBR specification. It's not very long, so it's quite easy to read. Okay.
Thank you, Etienne.
Yeah, you go ahead with firewalling and all the secure hardening of the platform.
Yes, so Etienne already mentioned this during a few slides. When we start the platform, one job we have to do is to tell that we want to assign a given peripheral, a given resource, whether to the secure context or the non-secure context. So for this is what we call the platform firewalling. We distinguish two times in the platform initialization, as we already said. We have the boot time, and we have the runtime that will remain available all along when the application is running. At boot time, we have two levels. The first one is the TFA BL2, so the trusted firmware for Cortex-A BL2, that will initialize two main components on STM32 MP1. The first one is the TZC, Trust Zone Controller, that is the DDR firewall. So thanks to the TZC, you can say that a given region will only be accessible from the secure world, and another one will only be able to be read-write by another set of masters on the system. So this is for the DDR. Then we have a very central peripheral on MP1 that is ETZPC, Extended Trust Zone Protection Controller. This one is really the peripheral that will allow to tell that this internal memory will be secure or not, and the same for a given set of peripherals. So the peripherals are there, the memories are there, and at boot time, the BL2 is already starting to initialize ETZPC partially, and then later on, when OPTI, the secure monitor, is started, it will complete this initialization, especially for the internal peripherals. So this is one aspect. After that, there is a peripheral that is very important for all products where you want to protect some secret and put in place of some protection in case of tampering, on physical tampering on the product. So the idea here is that when you detect an intrusion on your product, you are able to clear secrets that are stored in internal memories. So OPTI is responsible for the initialization of the TAMP peripheral that will protect all the secrets. Then we have another peripheral that is quite important. It is the BSEC for Boot and Security Controller. One important aspect of this peripheral is that it is the interface to all the OTP, one-time programmable fuses. So this is all the configuration, but also the fuses where the customer can put the keys, and so the root of trust that Etienne introduced earlier. The root of trust will really be inside those OTP fuses. And then the last important system peripheral here is RCC, Reset and Clock Controller. This is the peripheral that is responsible, as its name is telling it, for the reset and clock control for the world SOC. So inside RCC, we are able to isolate some configuration in the secure world and let direct access to the non-secure world for other aspects when we consider that they are not so sensible for the platform safety and correct execution. In turn, the RCC is connected to some regulator control that can be secured also. And as I said, the reset and the clock that are spread among all the peripherals on the platform. So this is the way STM32 MP1 firewalling is put in place at startup and remain valid when the application is running.
Yeah, we'll see a bit how this is, where this is configured. Actually, all this firewall configuration shall be loaded in the right interface in the system on chip. And Some are loaded by BL2, TFI BL2 bootloader, and some are loaded by OptiOS, as Gerald mentioned. And for configuring the firewall, actually being BL2 or Opti, we can distinguish between configurations that are inside the implementation and that inside the configuration of the package we've used, like a configuration of the Opti, or some configurations that are discovered by the firmware at boot time. And also there could be configuration done at runtime. Like at runtime, you could reassign a resource that was owned by the non-secure world and to have it owned by the secure world and or the other way around. Well, for this, we're based mainly on TFA and Opti repository. So these have few configurations that are expected built in the firmware itself, mainly the secure RAM locations and things like this. So there is a part of the firewall configurations that can be defined at build time by package configuration. But most of the platform's configuration, we tend to describe it using the device tree technology that allows to separate the device configuration from the device firmware executive part. So at boot time, both TFA BL2 and Opti do get the do discover from the device tree, from a device tree blob, what is the platform's configuration and how some of the resources should be assigned, whether some I2C or some SPI bus should be assigned to the secure world or to the non-secure world, and configure accordingly the right firewalls. And we have decided to not allow such assignment at runtime and changing the assignment at runtime, just to keep simple and clear who owns what and which resources is allocated to what, because due to dependencies, it could be quite tricky to be sure that all resources are really offloaded when we change the assignation from one world to another. So this is it for the firewalling configuration. I thought that there were some questions in the slide. So Gerald, I'll let you conclude, and I have a round.
I just answered a few questions in the chat, so I can conclude. So this presentation is to show you that STM32 MPU embedded software security is improving every year more and more. We want and we are contributing to the open source communities. So Linaro, as Etienne is one representative here, but also the Trusted Firmware, U-Boot, and Linux communities. All the past change that we did in STM32 MP1 boot chain and also the future one tends to achieve this goal. So this means that we want to improve the security on the platform, and we also want to improve how easy it is to configure this security on the platform for our customers. So this is what we could say in few words around this. Thanks for your attention. And if you have a question, don't hesitate, whether you can unmute your micro or in the chat.
Well, that's all. Well, thank you, Gerald. Thanks to all for all attendees, and thanks to all these that will view this video later. And we'll hope you use this device soon.
Thank you. Bye-bye.
Bye.